Right, so I'm going to explain how RSA works from a simple point of view, how the calculation happens. Okay, so with RSA, the core strength of it is that we have two prime numbers, and the strength of RSA is it's actually quite difficult for a computer to factorize back for the prime numbers that we've actually used once we multiply them together. Okay, so our core numbers that we have are P and Q. Okay, so the first thing that we actually do is that we multiply the values together to give us a value of n. So n is equal to P times Q. So in this example, we're using 11 and 3 as two prime numbers. Obviously, our prime numbers that we would use in a real life example will be much bigger than that. So in this case, we end up with 33. So the next thing we do is that we calculate a value called phi. And phi is equal to P minus 1 times Q minus 1. So in this case, we have 11 and 3. So then that becomes 10 times 2, which is 20. Okay. So what we must do now is to find a value of E which does not share any factor, any common factor in the value of phi. Okay, we write this as the greatest common denominator of phi and E is equal to 1. Okay, so the largest value that's a common factor between phi and E is 1. So within phi we can have 2, 4, 5, 10 and so on. So we cannot share any factors that will include, when we factorize out E, we cannot include any of these numbers. So let's select a value of 3. But we could also pick 6 doesn't work because that has a factor of 2. We could also pick 7 or 11 or 13. As long as it doesn't share a value with E. So our public key becomes E comma n. So we have 3 comma 33 is our public key. Now what we have is that we now must determine what the decryption key is. So D times E mod mod, and then we have our phi is equal to 1. So D times 3, we take the mod of 20 is equal to 1. So what we must do now is find the value of D which will make this true. So if we tried D equal to 1, no, that doesn't work. 2, 3, 4, 12 mod 20 gives 8, nope. 5, 6, 18 mod 20 gives 2, nope. 7 times 3 is 21, mod 20 is 1. So D equals 7 will work. But there are other D values which will work, and we can keep going round until we find a value that will make this part 21 mod 20. Okay, so we now have our decryption key. Our decryption key is 7. Our private key is 7 comma 33. Okay, so that gives us our keys. And if we just recap here, so we've calculated our keys. So our keys become our public key is 3,33, and our private key is 7,33. So the way that discrete logarithms work is that our cipher is equal to our message to the power of e mod n. So there's our e and there's our n. And then to decipher, we take the cipher, raise it to the power of d, and then take mod n, and it should work. So if we take a message of 4 to the power of 3 mod 33, let's do our calculation here. So that gives us 31. We then take 31 and we raise it to the power of d, which is a 7, and then take mod of 33. Then hopefully we'll find that the value is 4. So the value of 4 is what our message actually was there. Okay, so in this way we can select our public key and our private key, and we share n and we share e. The strength of it, of course, is we're giving away our n value. So if someone can factorize into the prime numbers which were used in that, then they can obviously crack our encryption. Okay, so there should be examples given on this page here that you can actually have a look at and see how it works. The main thing to remember is the selection of E, so that it has no common factors with phi, and then in the selection of the private key, which is to make sure that d times e mod phi gives us 1. Okay, thanks.